Hello guys, welcome back to my channel, and today we'll be doing an integral finally that has a lot of drama in it. So let's get to it. So we have our problem, let's call it I, that's defined as the integral from 0 to 1 of pi over 4 minus the inverse tangent of x divided by 1 minus x squared, and there's obviously the dx. Now looking at the integrand, we have an inverse tangent and um, a square term in the denominator. So it could look like a very good candidate for a trig substitution. So we could actually choose x to be tan theta because of this inverse tangent, because the inverse tangent of the tangent of theta will be just theta. But the only problem is in the denominator we have 1 minus x squared, which is 1 minus tan squared theta if we do this substitution. And this doesn't amount to much because we don't have any square identity that has 1 minus tan squared of theta. We have 1 minus cosine squared of theta. We have 1 minus sine squared of theta being equal to, in this case, sine squared theta, and in this case cosine squared theta. So trig substitution seems like a pretty bad idea, because unless we had something like 1 plus x squared in the denominator instead of something like this, then x equals tan theta would have made sense. So it doesn't seem like a really good idea to use trigonometric substitution. So let's forget that. Why don't we try exploiting symmetry? Well, if we try to do that, instead of x we'll have to substitute 1 plus 0 minus x. So we'll have the inverse tangent of, say, 1 minus x, and in the denominator we'll have 1 minus x, the whole thing squared. And now this would result in 1 minus 1 plus 2x minus x squared. And the denominator isn't, exploiting symmetry isn't going to help much, because look at the form of the denominator. It's probably even uglier than before. It's probably harder to manipulate than before. So exploiting symmetry is out of the question. So one thing that we can try to do is use some identities, because we have an inverse tangent here. So are there any inverse trigonometric identities that we can refer back to? Well, for starters, we have a pi over 4, right? Can we write that in terms of an inverse tangent? Because this bracket arrangement seems kind of suggestive. So, well, we certainly have an inverse tangent value for the pi over 4. We have inverse tangent of 1 being equal to pi over 4. And you will see in a minute why writing pi over 4 as inverse tangent of 1 is useful. So we have the inverse tangent of 1 minus the inverse tangent of x and a dx, and then in the denominator we have 1 minus x squared as it is. Now why is writing this as a difference of inverse tangents useful? It's because of the following fact. It's because we have this great identity. Say we have the inverse tangent of A minus the inverse tangent of B. That's nothing but the inverse tangent of A minus B upon 1 plus A times B. And in our case, A equals 1 and B equals x. So we'll just have the inverse tangent of 1 minus x divided by 1 plus a is 1 x and b is x. So 1 times x is nothing but x. So because of this powerful identity on the inverse tangents, we can actually convert our integral into the integral from 0 to 1. Then instead of this difference, we can write this. So we have the inverse tangent of 1 minus x divided by 1 plus x, and in the denominator we have 1 minus x squared and then a dx on top. Now what can we do? Well, before we can even think of substituting any value, I would like to remind you of two other identities on trigonometric functions. So we basically have two identities on the cosine function. So say we have 1 minus cosine of theta. This becomes 2 times sine squared of, where you half the angle, theta by 2. And if you have say 1 plus cosine of theta, this is just 2 times cosine squared then half the angle, theta by 2. So in place of theta, say we had 2 theta, then on halving 2 theta we'll just have a theta. So 1 minus cosine of 2 theta, just to give you perspective, is 2 times sine squared of theta, because half of 2 theta is just a theta. So we can definitely be using these facts in a short period of time, and that's because we'll be really using these facts. That's because we're gonna make this great substitution now. We're gonna be letting x equal a cosine of theta, and I'll complete the substitution on the next page. See you there. So we simplify our integral to the integral from 0 to 1 of the inverse tangent of 1 minus x over 1 plus x times dx over 1 minus x squared. And then I said that let x equal the cosine of theta, because if you remember what are the identities I showed you on the cosine of a few minutes ago, we have those conditions in the numerator of the argument and the denominator of the argument, and then 1 minus cosine squared theta is nothing but sine squared theta. So we can be using those powerful facts together. So dx is nothing but negative sine theta d theta, and when x is 0, cosine of theta is 0. So theta is the cosine inverse of 0, which is a pi over 2, because if you plug in pi over 2 instead of theta in the cosine and then take the cosine of it, that you'll obtain a 0. And when x equals 1, that's to say that cosine theta equals 1. So theta is the cosine inverse of 1, and that's a 0. So great, we have all our information that we need for our classic substitution. So instead of 0, we have a pi over 2 here, and then instead of the 1 we have a 0, and the negative sign of this negative sine theta can be taken outside, and we have the tan inverse of 1 minus cos theta over 1 plus cos theta, and then instead of the dx we have negative sine theta d theta. We took the negative outside, so we have sine theta d theta, but divided by 1 minus cosine squared theta. now we can suck up the negative and then flip the upper and lower bounds of integration. So we have the integral from 0 to pi over 2 of the inverse tangent. Now we can directly use the identities that I discussed with you in the last page. So we have 2 sine squared then half the angle theta by 2 divided by 2 cosine squared half the angle theta by 2, and then we have a sine theta d theta over 1 minus cosine squared theta is sine squared theta. Okay, great. So these 2's are going to cancel out and one of these sine thetas are going to cancel out. So we have integral from 0 to pi over 2 of inverse tangent of, we have a sine squared theta by 2 divided by a cosine squared theta by 2, which is nothing but a tangent squared theta by 2, and we just have a sine theta in the denominator, and I won't forget the d theta. Now we have one problem, and the problem is we have a half angle in the argument and we have twice of the half angle or the full angle in the denominator present outside the inverse tangent. So we can actually convert this sine theta into half angle of tan theta. We have an identity for that. So a lot of identities in this video. So we have the great identity, say sine of theta is equal to 2 times tan of half the angle theta by 2 divided by 1 plus tan squared theta by 2. So we can directly use this formula now. So we have the integral from 0 to pi over 2 of the inverse tangent of tan squared theta by 2, and then instead of this sine theta we can write 2 tan theta by 2 was in the numerator, so 2 tan of theta by 2, and then the denominator goes on top, gets flipped basically to 1 plus tan squared theta by 2, and don't forget the d theta. Well, what's 1 plus tan squared theta by 2? That's right, a secant squared theta by 2. So we have the integral from 0 to pi over 2 of the inverse tangent of tan squared theta by 2 over 2 times tan of theta by 2, and then we have a secant squared theta by 2 and a d theta. So now noticing the secant squared theta by 2, that looks like the derivative of the tangent function, right? Secant squared of a variable is the derivative of the tan of that function. So noticing that in the numerator, this looks like it's asking for another substitution where we let say a variable equal tan of theta, because we have the derivative of the derivative of tan in the numerator. So that's really calling for a substitution number 2. So let's do that on a fresh page and I'll see you there. So we have the following expression, and I'm saying that let's do a classic u substitution. So let u equal tan squared theta by 2. I mean, if you were paying attention on the last page, you might notice that I claimed to do a substitution where u equal tan of theta. But why am I taking a tan squared here? That's because if we take u equals tan theta, we'll have u squared in the argument of the inverse tangent, and it would be wise to want to avoid a square in the argument of a function in most general cases of integration. So and you will see in a minute why how helpful this thing is. So we have du being equal to well, we can use the power rule. We have 2 times tan of theta by 2 times the derivative of the inside function, which was tan, so secant squared of the variable, and then the derivative of theta by 2 is nothing but a half. We basically chain rule 2 times. So chain rule 2 times because we had the tan of theta by 2 being squared first. So we first used the power rule on that, and then we had a tan of theta by 2 inside. So we used the derivative of the tan being secant squared of the inside part, and then the derivative of the inside part, because it wasn't just plain theta, right? It was theta by 2. So now notice that this 2 and this 2 cancel out, and sorry, I forgot the d theta. So we have du being equal to tangent of theta by 2 times the secant squared of theta by 2 d theta. Now we want to actually find values for our upper and lower bounds. So when theta equals 0, we have u being equal to the tan squared of 0 by 2. So tan squared of 0 is 0. And when theta say is equal to pi over 2, we have u being equal to tan squared of pi over 2 divided by 2, which is a pi over 4, and the tan of pi over 4, the whole thing squared, that's what a tan squared is, right? Is nothing but, so tan of pi over 4 is 1 squared is 1. So we have our upper and lower bounds also. So basically I can be rewritten as the integral from 0 to 1 now, we just did that here, of the inverse tangent of u, because we had a tan squared theta by 2, so we call that u, and then let's just write the denominator as it is in the theta world. So 2 times tan of theta by 2, and then we also have the equivalent of the du, right, of the d theta, right? So why don't we kind of rearrange everything? So well, we have a secant squared theta by 2 and a d theta, so let's keep this part intact and then divide everything by tan theta by 2. So we have du over tan of theta by 2 being equal to secant squared theta by 2 d theta, which is basically the remaining part of our numerator. So we have basically secant squared theta by 2 times d theta is basically du over the tan of theta by 2. Now notice that we can take the half outside. We have the inverse tangent of u, and we have 2 tan theta by 2 is being multiplied together. So we have tan squared theta by 2. We have a du. Now notice that what was our u? Our u was nothing but tan squared theta by 2, right? And we have exactly that thing in the denominator now. So now you see why my substitution was quite powerful in this case. It's because we not only have a linear term in the argument of the inverse tangent, but we also converted everything in a much easier form that we can work with. So we have the integral from 0 to 1 of the inverse tangent of u over u, because tan squared theta by 2 is u, and we have a du. Well, wow. Now it seems looking at the form of the integrand, having a linear term in the place of the argument of the inverse tangent, it looks like it's calling for us to use the Taylor series for inverse tangent. So let's do that on a fresh page. That's like our end game now. So we basically simplified I to be the integral from 0 to 1, and we have a half outside of the inverse tangent of u over u du. Now I promised to use the Taylor series for the inverse tangent function. So let me remind you what the Taylor series for the inverse tangent really was. So if we had the inverse tangent of say x, that would be the sum from n equals 0 to infinity of negative 1 to the nth power times x to the 2n plus 1th power divided by 2n plus 1. So it's pretty neat, and the great part is we don't have any factorials in the denominator. Otherwise, even after integration, we couldn't make any real sense of the infinite series that we obtained. Linear terms are best to work with. So we can write I as half of the integral from 0 to 1 of the sum now from n equals 0 to infinity of minus 1 to the nth power times u, because our original variable was u, to the 2n plus 1th power divided by 2n plus 1, and we have a du, so don't forget that. Now, as most of our videos, we assume a uniform convergence, and if you're wondering why we do that, if you're like new to my channel and you're like wondering why we do that, it's because that allows us to interchange the limit and the infinite sum, because in most cases we couldn't be able to do that, wouldn't be able to do that. We have to uh, justify our switching on the basis of the dominant convergence theorem, Fubini-Tonelli and all that. So we can assume uniform convergence for now. So we have half of the sum from n equals 0 to infinity, and I'll take outside all the terms that have only an n. So minus 1 to the n divided by 2n plus 1, and an integral from 0 to 1 of u to the 2n. Well, I forgot the u in the denominator, guys. There was this u in the denominator, right? I forgot that, sorry, really sorry. So we have a 2, right? And when the 2 u raised to 2n plus 1 is divided by a u, we just have u raised to 2n, right? Because the first power cancels out. We have u raised to 2n, we have a du. So now we can actually calculate our integral. We'll have to use our power rule. So power plus 1 with minus 1 to the n as it is, power plus 1, u raised to 2n plus 1, and then we divide by the new power. So we divide by 2n plus 1, and we already have a 2n plus 1 in the denominator. So we have 2n plus 1 times a 2n plus 1. So 2n plus 1 squared. But don't forget to evaluate that from 0 to 1, because it's a definite integral. Now plugging in our upper and lower bounds, we have half of the sum from n equals 0 to infinity of minus 1 to the n, and when we plug in 1 in the place of u, we have 1 to the 2n plus 1 power. 1 to the any power is just 1 divided by 2n plus 1, the whole thing squared. And when we plug in 0 in the place of u, we have 0 divided by something, so that's 0 entirely. Good riddance, right? Well, we can ignore the 0. We have half of the sum from n equals 0 to infinity of minus 1 to the n divided by 2n plus 1, the whole thing squared. Now what does this remind us of? This part, excluding the half, is our Catalan's constant, right? So we can write that as half of g, where g is our Catalan's constant. So that's a really beautiful result if you ask me. Half of the Catalan's constant. So to conclude, whatever the drama we did in this video about integrals, we had originally a problem, integral from 0 to 1 of pi over 4 minus the inverse tangent of x divided by 1 minus x squared, and we had a dx2. That just evaluated to half of the sum from n equals 0 to infinity of minus 1 to the nth power over 2n plus 1, the whole thing squared. And we know that this was Catalan's constant, so we have half of Catalan's constant, g. So that's a pretty nice result, and it's actually like one of the previous videos that I did of, I think, the innocent looking integral of x over cos of x. I think I did that. Yeah, integral of x over cos of x, and we obtained a similar result. I think we obtained a 2 times Catalan's constant in that one. So you know, these integrals are actually some equivalent forms of each other. You can obtain the other by, you know, using a specific type of substitution or rearranging the terms in a certain way. But that's it for this video, guys. So it seems it's time to wind up. Please like, share and subscribe to my channel. Recommend me to your number 5 friends or whoever would be interested in this kind of stuff. And stay home, stay safe, have a great day. Peace out.